Let me start by thanking the organizers for the invitation and the chance to speak here. Actually, before I begin, I want to make an announcement. So I'll be going to the airport tomorrow afternoon, and I'm thinking of booking a taxi to leave at 4 p.m. If anyone else is going to the airport around the same time, I'm happy to share the ride, and please let me know after the talk. Okay. So I'm going to talk about a joint work with Hiraku Atobe, who is a graduate student of Ichino at Kyoto. Okay, so the topic I'm going to talk on is on Theta correspondence. So let me just recall the setup briefly. I take F to be a p-adic field. Let me take either a quadratic extension of F or just F itself. Then I can look at the notion of a Hermitian space over E. So epsilon is plus or minus 1. And let me take W to be an analogous space, but with the opposite sign. So minus epsilon Hermitian space. So for example, when E is equals to F, and I take epsilon equals to 1, then I'm saying that V is a quadratic space, and W is a symplectic space. So then I can consider the isometry groups for these two spaces. And this pair of groups is what is called a dual pair. So these are the unitary groups for the relevant Hermitian or skew Hermitian space. Okay, and I guess the point is that this pair of groups acts on a certain representation that depend, among other things, on an additive character of the base field F. Okay, so it's a so-called Weil representation. Okay, and so the theory of Theta correspondence concerns the decomposition of this omega as a representation of UV and UW. Okay, so to formulate more precisely, if you give me a representation of, say, one of the group, then I can look at the so-called maximal pi isotypic quotient of this guy. And so it's supposed to be pi isotypic, so it has a form, some multiplicity space times pi. And that multiplicity space, we just call it data of pi. And whatever it is a representation of UV, since the action of UV commutes with that of UW. So I guess one knows something about this, that in fact it is a finite length smooth representation of UV. And of course it could be 0. If pi doesn't appear, then of course the pi isotypic quotient is 0. Okay, so it's maybe 0. Maybe 0. Okay. Okay. All right. So in fact, in this talk, actually, I will just focus on one example. So the example which I will just focus on is I'm going to take E equals to F. I'm going to take epsilon equals to 1. So I'm looking at quadratic space and symplectic space. So V is quadratic. W is symplectic. And I'm going to assume that the dimension of V is odd. Then, of course, UV is the orthogonal group, right? So, and UW it should be is the symplectic group, okay? But for some technical reasons, I have to work with a double cover because of this odd. Okay. Anyhow, this is the example I want to keep in mind, and I will just specialize the discussion to this case. After all, we saw this group in the first talk. So, okay. Now, okay. So in this context, of course, the question then is: given pi, what can you say about this guy? So there is a so-called Hall duality theorem that says that so either it is zero. It could be zero, or else it has a unique irreducible quotient. Which we will denote by a small data of pi. Okay, I guess this goes back to Hall himself, and Walsh-Berger and Muich did a lot of work on it, and only a couple of years ago it was completely completed by Takeda and myself. So anyhow, we have this. Okay, so at this point, it's natural to consider the following problems. And so these are the two problems I want to consider today. Okay, so, well, you know whether this, so this is either zero or is basically irreducible. So it's the first question you might ask, or the first problem you might consider, is to determine when this guy is a non-zero. Okay. And the second problem, which I want to consider, is just a permutation of the first problem. Determine this representation precisely when it is non-zero. Okay. So those are the two problems. I should use this. Okay, so hope you'll stop. Okay, so that's good. So those are the two problems I want to discuss, and I'm going to, yeah. So as I said, I'm going to discuss the problem only for that example. So the MP and the odd orthogonal group, and so the point of this talk is, so the goal is to answer or to address this problem, address A and B for tempered representation pi. Of course, since I'm working with MP of, so this is a irreducible representation of MPW, right? And so since I'm working with this metaplectic group, my representations are always assumed to be genuine. Okay, and so I would like to address this problem for tempered pi in terms of the local Langlands correspondence. Okay, because if I want to determine what the representation data pi is, you have to tell me what it is in some way. Okay, so I'm going to make use of the local Langlands correspondence as a classification scheme for irreducible representations. Okay, so now maybe let me talk about a reformulation of the first problem, which is just to decide whether the vanishing or non-vanishing of the data leaf. Okay, so instead of fixing, one dual pair like that, okay, I'm going to, so I will fix this UW, and I'm going to look at all possible V's. Okay? So recall that because I'm looking at odd quadratic spaces, odd dimensional quadratic spaces, so for any odd number, say 2n plus 1, there exists two quadratic spaces of dimension 2n plus 1 and discriminant 1. Okay, so what are they? Well, so maybe I will write them like that. Plus and minus. Okay, so this is the split quadratic space. So it has a maximal isotropic subspace of dimension n. The other one is a non-split. Okay, so they're just these two, and okay, and of course, as n varies, you get a whole family of the plus spaces and a whole family of the minus space. So, for example, to get this guy from this guy, you simply add a hyperbolic plane, right? Okay. All right. So by adding hyperbolic planes, so maybe you start with a 1 dimension quadratic space, you keep adding hyperbolic planes, you get 3 dimension, 5 dimension, and so on. You are going to get a whole tower. So I will call this the Witt tower. Maybe the plus Witt tower of odd dimensional quadratic space of discriminant 1. And similarly here, I'm going to get the minus, okay, tower. I don't know, maybe. So it's just a collection of all these V plus 2n plus 1 as n varies. Okay, so maybe pictorially, so the situation is that I'm fixing this group. I have my representation, and now I have my two Witt towers here, the plus and the minus. So I have, along this tower, I have various orthogonal groups, right? I mean, somehow they're getting bigger and bigger. So similarly on this side, there it goes up. Okay, and so I can consider I can take any of these groups, and I have the dual pair, and I can consider the data leaf of pi to just any member of these two towers. Okay, so obviously the point is for any given arrow, I want to know whether pi is sent to 0 or not. That is the first problem. Okay, and okay, so for the reason for doing it this of setting things up this way is that there's a result of Cutler, sometimes called persistence, that if the data leaf, I forget about this, to any of these spaces, say, yeah, so I'm going to write it as plus of 2r plus 1 pi, something like that. Okay. So if any of these guys is not, if this is not 0, okay, then it continues to be non-zero for all k bigger or equals to r. Okay, in other words, suppose you know that this guy, the data leaf of pi to this group is not 0, then as you go up to bigger and bigger groups here, the data leaf continues to be not 0. Okay? Now, after you know this, then of course the whole problem A becomes reduced to asking where is the first place in this tower where the leaf is not 0. Because once you know where the first place is, you know it is non-zero as you go further up the tower. Okay? So I guess this motivates us to define the notion of the first occurrence of pi in a given Witt tower. Okay? So, okay, well, how I'm going to call it. Yeah, okay, so this motivates us to, let's do it over here to make the following definition. The notion of first occurrence of pi, which is that let's define m plus of pi to be the minimum of k such that the data leaf to the O2k plus 1 is not 0. And likewise, for the minus tower. Okay. So problem A is equivalent to determining these two numbers. Right? Because if you know what these two numbers are for both this tower, you know it completely. Okay. Now, okay, so there are two numbers you have to compute. But thanks to a result known as the conservation relation. Okay. So this is used to be a conjecture of Kutler and Rallis, and now it's a theorem of Bingyong Shun and Chen Bo Zhu that tells you that one has the following identity. Oh, I see. I think I'm going to modify my definition a bit. I would like this m plus and m minus to be the dimension of the okay, so maybe I write 2k plus 1. I'd like it to be the dimension of the quadratic space. Okay, doesn't matter. Okay, anyhow, then with that modification, where dimension of W is 2n. Okay, so I mean, that's what this n here. Okay, so I'm working with MP2n, let's say. Okay, so this is good because this is telling us instead of computing two numbers, you just have to compute one number, right? Problem A is, if you can determine one, you can determine the other. Moreover, note that these m plus and m minus are odd numbers, right? So if they were to add up to a number divisible by 4, they cannot be equal. Okay, so this implies in particular that m plus, it cannot be equals to m minus. Okay? So one of them has to be bigger than the other. And so let's make a definition. I'm going to just call m down, okay, pi to be the minimum of these two. Okay, and I'm going to call m up, pi to be the other guy. Okay, so why down and up is because, suppose m plus is the smaller, okay, then, maybe I say it over here. So I mentioned that they are not equal. Okay, so if they were equal, then okay. So let me write over here. So m down of pi, it's going to be of the form 2n plus 1 minus some delta, and m up pi is 2n plus 3 plus some delta. Wait, because the closest that it can be is if delta is 0, right? Then they can't be equal. Okay. So this means that so why down is because I'm thinking of the leaf from MP2n to, if this were 2n plus 1, then this is the sort of equal size case. So for the down tower, so in one tower, the leaf will go below the equal rank case, okay? And on the other tower, it's forced to go up, okay? Okay, so anyhow, the point is this problem A is equivalent to answering the following questions. So which is the so-called down tower? And then what is the value of m down pi? Okay, it's just reformulating the question. Okay. All right. And so I think this is the answers will be formulated in response to these two questions, okay, for problem A. Okay. Come to this side. No, in fact, I wanted to use. Okay, so now I say that the answers will be formulated in terms of the local Langlands correspondence. So let me briefly recall. What that is. I think something is happening, even though you don't see it yet. So. Okay. This is going to be my local Langlands correspondence board. I hope it's big enough. Okay, so okay, so let me start with that. Actually, you already hear it in the previous talk, I think. But okay, so the local Langlands correspondence for SO2n plus 1. So we are interested in the irreducible representations of these two special orthogonal groups. Right? Okay, and the local Langlands correspondence due to Arthur, at least for the split group, and also again Moglen has also done the inner forms case. Okay, so I will just take this as a given. Okay, okay, so it's in bijection with a set of pairs, phi and eta, where so phi is a what we typically call a Langlands parameter. Right, a map from the Wedelin group to SP2NC, and eta is a irreducible character of the component group. So let's go as phi, okay, which appears in Asushi's talk just now. So let me just leave it. Okay, so as I said, this is a classification scheme for a representation, right? So if you give me a representation of either of these two, it has a ID number, or the way I like to think of it is think of it as the last name and first name of my representation. Okay. So I think of this as the last name. I think of this as the first name. Okay, so for me, it's just some label that I give to a representation that allow me to identify what the representation is. Okay, but of course, in the problems that we are addressing, we are not really interested in these two groups, right? We are interested in the MP2N. We are interested in the orthogonal group, not special orthogonal group. Okay, but of course, however, of course, this group is nothing but SO2N plus 1 cross plus minus 1. Okay. So it's very easy to classify the representation of this group if you already know the classification for this one. Okay? Okay, there are two ways of extending an irreducible representation to this product. Either you let this part be the trivial character or the non-trivial character, and you can indicate that by a sign. Okay. So I have a similar thing here. So it is so instead of a pair, you have a triple where this epsilon is plus or minus. Okay. Okay. So you can think of this. This is just a cloning. Very often we will be able to clone ourselves. So every representation here clones itself another copy. Okay? But of course, you can tell the plus is the original copy and the minus is the clone one. Okay? So that is the LLC for this group, or orthogonal group. Okay. Now, I also want the LLC for MP2N. And as Asushi explained in his talk earlier, this is obtained by the local Shimura correspondence. So we have, there's a bijection depending on using data correspondence, if you wish, that between this and that. And so you can compose this bijection with that bijection and get a classification of. So this would be what I call the LLC for MP2N. Okay. I'll use this as a. Okay, so in other words, these two sets, which are, after all, in bijection, are classified by the same things. Okay, so now I think the upshot is now, given any guy here and any guy there, I have names for them. Okay, and I would like to answer problems, address problem A and B using those names. Okay, so. So now let me formulate the main results using these names. Okay. So we address these problems A and B for all tempered representations. But in this talk, I will just formulate the results for discrete series representation because it's slightly cleaner. Okay, so let me just remind you for the discrete series, they will correspond to so-called discrete phi, right? So what is a discrete phi? A discrete phi is basically a multiplicity free. So a multiplicity free. Right? So phi is a map from the Wedelin group to SP2NC. So I can think of it as a 2n-dimensional representation. And I can decompose that representation into irreducible pieces. And I call such a phi discrete if it is a multiplicity free sum of symplectic summands. Okay, symplectic summands just means each of the phi I are themselves takes value in some smaller symplectic group. Okay, so for such a thing, one can, as Atsushi described earlier, the component group is just a Z mod 2Z vector space equipped with a canonical basis, one corresponding to each summand phi I. Okay, so this means that if I have an irreducible character eta, you just have to tell me so if this is an indexing set I, right, you just have to tell me what value it takes at each of these basis vectors. And these things are in plus or minus 1. Right? So a character eta is just a bunch of signs, a sequence of signs. Okay. Yeah, so since there are so many signs, okay, maybe if you don't like to think of it as signs, you can think of it using Michael Harris' language, black and white keys. Black or white, okay, so something like that. Okay, so that's just discrete series case. And this is 2. Okay, now I can formulate the main results. Okay, so since I have two problems, A and B, I will label my theorems accordingly. Okay, so the first, for problem A, I have reformulated it in terms of two questions, right? The first one is which tower is going down tower and which tower is going up. Is going down tower if and only if. So I have to decide which epsilon is for pi. Okay, if epsilon is just eta pi. So okay, maybe I say pi has this name. Okay, so of z phi. Okay. So as I said, I'm just going to formulate the theorems for a pi discrete series. Okay. Okay, so what is this guy? I mean, this guy is the same Z that appear in Atsushi's talk. It is basically image of the element -1 in sp2nc in the component group. But in terms of this basis element, it's just the sum of the AIs. Okay, because I say the component group was this Z mod 2Z vector space with this basis AI, so I just add it up. So okay. Okay, so that determines that. Okay, 2. So now what I have to do next is to tell you what is m down. How far does it drop down? Okay, this pi. Okay, so let's set m down of pi to be is 2n plus 1 minus delta pi, let's say. Okay, that defines. Then delta pi is the minimum of a set T. Okay, maybe just to distinguish this minimum, I call it L pi. So what is T? T is a set of integers. So all even L bigger than 0. such that something happened, but maybe I want to put 0 in, so okay, let's put bigger equals to 0, such that that satisfies 3 conditions. First is a chain condition that says that this parameter, the last name of pi, has to contain so S2, S4, SL are the so S2 is the 2-dimensional irreducible representation of SL2C, because we are talking about the Wedelin group, so there is a SL2C in there, so it's a 4-dimension and so on. It's an initial condition. So since it contains this, so each of these guys is going to contribute a basis vector to the component group. I'm going to call the basis vector E, E2, E4, EL, okay? So eta of E2 has to be +1, okay? And then the other last condition is alternating, that eta of EI is negative of 2i +2. Okay. As I range from, I mean, the EI range over this chain, the basis for this chain. Okay. So maybe 0 bigger equals to I, less than equals to something. Okay. Okay. The EI is the basis vector corresponding to each of these summands. Because my parameter, which is a discrete series parameter, contains these guys, right? So in the top dot, I say that S phi is a Z mod 2Z vector space with a canonical basis indexed by the summands of phi. So each of these summands will contribute one basis vector, right? And I'm saying my character has to look this way. So of course I can combine these two conditions by saying that, you know, if I write down this chain S2, S4 to SL, the first name has to look like that. Just alternate.
Does this chain necessarily contain them without gaps like S2, S4, S6?
Yes, that's what I mean by chain. I mean that. I mean.
But can it contain more representations?
Oh no, it could contain more. But you see, suppose that in fact this guy contains SL plus 2, right? But let's say it's not. Let's say the last sign here is plus, okay? And let's say it contains SL plus 2, but it's not alternating anymore. Then I don't put this L plus 2 in here, right?
That's another chain. Then SL plus 2 will be part of the different chain.
No, I mean, it's just, so the question was just whether L plus 2 is in this set. And the answer is not. Because, yeah, so that's why maybe.
So the chain starts always at 2.
It starts as 2, yeah. It always starts at 2. I mean, it can go on further, but, you know, so it's possible that, you know, the eta just takes plus, 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 plus everywhere. For example, if it's like some generic for the particular Whittaker datum, then it's associated with the trivial character of component group, then it's plus, then of course there will be nothing in this set except 0.
So do you mean this is contained in S phi?
Which is contained in S phi?
The containment.
Oh, you mean this?
Yeah.
No, this representation of SL2. Sorry, phi is a representation of the Wedelin group. I mean, phi is an L parameter for, you know, it's a map from Wedelin group to SP2N, which I think of as a 2n dimensional representation. I break it into irreducibles, and I'm saying that I would like to see this chain of irreducibles. These are irreducibles of SL2, the SL2 part of the lin part of the Wedelin.
And those even numbers in the dimensions are related essentially to dimensions?
This?
No, the numbers in the chain.
Yeah, that's right. So SK is the k-dimensional irreducible representation of SL2C.
Oh, so you're saying phi restricted to the Wedelin invariably?
No. Phi as a representation of Wedelin group. Okay, when I write this, I mean trivial character of V part tensor.
Oh,
Yeah, okay. Oh yeah, max, that's right. Max, hey, thank you.
This set is empty?
Okay, that's why maybe I should write it this way. Forget about this. Union, 0. I mean, it's possible that this delta is 0, so the first leaf is 2n plus 1, and the other guy is 2n plus 3. Okay, so this addresses problem A because it tells you which is the going down tower. It tells you what is the value of this m down, and the answer is all expressed in terms of these two guys. Okay. All right, so now let's formulate a theorem B. Okay, so now problem B is about telling me when it is not 0 what it is. Okay, I will just formulate a special case. Okay, so for example, I mean I should answer it for both towers, right? Because whatever is not 0, I should tell you what it is. But let me just consider only the going down tower. Okay, and in fact, let me only consider. So I know that, okay, so 2m plus 1. So I already focus on going down. So I will drop the label of the sign here. Okay. Pi with 2n plus 1 minus delta pi. This is the first occurrence. Okay, so maybe just draw a picture. It will be clear. So I guess I have my pi. This is on MP2n. I know, let's say the going down tower is here, and the first leaf is to this O 2n plus 1 minus delta pi. Okay, so I know below down here it leads to 0. So it is non-zero everywhere, and I should tell you what representation I get at each step. However, let me just to give you a flavor of the answer, I'm just going to describe the leaf of pi up to the equal rank case. I mean, there's something up there, but up there is actually easy to describe. The interesting part maybe is here. So I'm restricting my 2m plus 1 to be between the first occurrence and the equal rank. Okay, I'll just formulate it in this region, so to speak. Okay, so this guy had a last name, had a first name, and had a sign that because it's an orthogonal group. Yeah, and of course the dimension of this Wedelin representation phi prime is 2m, because whatever this is a representation of O2m plus 1. Okay, so I have to tell you what these three things are. Let's start with epsilon prime. I want to tell you this in terms of the name of pi, right? Phi and eta. Yeah, so this is the. So this is the same number as the step one. Okay, times. This root number 2. Phi prime is phi. So I have this is 2m dimensional, and m is less than n. So I have to take away something. I mean, I take away whatever is necessary to make the dimension right. Okay. Now, why am I allowed to take this away? Well, because I'm assuming this is non-zero. Right? I mean, I know this is non-zero. So by this chain condition, I know phi contains this guy. So I can take it away. So this is not some virtual representation. It's actual. Phi contains this thing, and I remove it. And finally, actually, as a consequence of this, you see that this phi prime it just looks like phi, except this summand is missing. Okay? So this means that you can think of the component group of phi prime naturally as a sub, because you're just removing one basis, so to speak. Right? Because this guy is one of the Z mod 2s, and I'm just dropping it. Okay? So if I were to tell you what eta prime is as a character of this, I have to tell you what value it takes at each of those basis elements, different from this one that I remove. Okay? But I can compare that with the value of eta on that basis element. So I have an AI in here, and it also lives in there. Okay, so of course this AI corresponds to some summand phi I in phi, okay, which is different from this guy that I remove. Okay, so this is a, it's given by a root number. (2m minus 2m minus 1). Okay, but in fact this root number is very easy to calculate, so let me write more explicitly. What this is. Okay, so that product of a local root number, well, it's either +1 or -1. And if phi I is S2k, else, for k between this. Okay. Okay. So basically we are saying that eta prime looks like eta, except you change it at some basis, some Z mod 2s you change it. Which are the ones that you change? Well, we know our phi contains and maybe more, okay? But so this was the guy that I removed to get phi prime. Okay? This is 2n minus 2m. Right? So what this is saying, where do I get, sorry, this is +1, this is -1. Where do I get a change of sign is precisely here. Yeah, okay, when I write this, I mean trivial tensor as of 2. Okay. Right? So I know my guy contains this change at least up to this point. There could be more. I'm removing this to get phi prime. And I mean, it could be non-trivial or go up. No, it's trivial. When I read S2k, I always mean just the S2k is a representation of Wedelin group where the Weil group acts trivially. Okay? So I'm just changing the sign on this, the chain up to the point where I remove it. That's what this is saying. Okay, anyhow. Okay. So those are the theorems. So the last part I wanted to sketch the proof or certain parts of these theorems. So for me, the most fun part of the proof is applying the local Gross-Prasad conjecture to get some information. So I want to explain that. Okay. It will not prove the theorems completely, but you will see, for example, how you might get part 3 of this. Okay, okay, so using the local Gross-Prasad. So of course, I assume the local Gross-Prasad is known, and it is kind of known, right? I mean, so for the orthogonal case or special orthogonal case, it was due to Ross-Berger and Guglen-Ross-Berger, and but I also need the case of the symplectic-metaplectic groups, the so-called Foro-Jacobi models, and that is due to Atobe in his thesis. All right, so I want to explain how you get theorem B part 3 using the Gross-Prasad conjecture. Okay, so it basically is something like that. Okay, so I have pi on MP2N. So let sigma be the data leaf that I am considering. It's not 0. Okay, so now I'm going to draw a seesaw diagram. This thing has a mu too, so let's do O2m plus 2 O. Okay, not being very precise, but anyhow, there's such a seesaw diagram. Okay, now my sigma is a representation here. So its data leaf to MP2N is pi. Pi is data leaf of sigma. Okay. And now, okay, let me do it over here. I'm going to choose a tau irreducible tempered representation of SP2N such that, so my tau, whatever it is living here. Hom SP2N, let's see, maybe I want to put tau check. Okay. So pi tensor, let's say the representation check, tau check is not 0. Okay, this Hom space, I guess I can just rearrange a bit. So something like that, rearrange a bit. Okay. All right. So so first I claim one can find such a tau. Okay. Why? Just in some sense by considering integrals of matrix coefficients. Okay. One can find such a tau. Suppose you have such a tau. Then you will have this seesaw identity you can use. This Hom space is equal to O2m plus 1. Okay. So you will have the data leaf of tau check here. And a 6 sigma, I guess, something like that. Okay, so you have these two. The seesaw identity tells that this Hom space is that. This is tau is chosen so that this is not 0. Okay, but note that this Hom space is nothing but the tau Hom spaces that appears in the local Gross-Prasad conjecture for symplectic-metaplectic groups, so-called Fourier-Jacobi model. And this guy is basically Besser. So because I know the local Gross-Prasad conjecture, the local Gross-Prasad conjecture will tell you rather precisely what the first names of these representations are. Okay? I don't care about tau. Tau is just some auxiliary choice. Okay? So GP tells me that something about the first name of pi, and so this is GP for Fourier-Jacobi, and using GP for Besser, I know something about this. Okay, so what does it tell you? So for this one, I'm going to drop the half because all my root numbers are evaluated at half. Okay, so you get something like that. Of course, you say this depends on this auxiliary choice tau. Of course, it has to be. It has to depend. Okay, and I don't know what it is, but for the other guy, you get okay. So for this other guy, the eta sigma should be described using some root number that depend on the last name of this guy, the L parameter of this guy. Okay, so in doing this argument, I have to assume I already have done part 2. Okay, part 2 tells me how last names correspond. Okay, so I need to know that this, I mean, this is basically this guy minus, I think, something like that, I hope, okay, something like that. I mean, you have to get the dimension right, because this guy is 2n plus 1. I want to end up with 2m plus 2. Maybe this works, okay? All right, so I should have written tensor of this thing, I guess. But because this is equal to that, so I will get okay. So the point is, I'm interested in comparing them. So when I compare this part of tensor, I will get what I claim in part 3. Okay, so so from this you can deduce this alternating condition that there was. But okay, let me stop now. Yeah. Thanks.
Are there any questions or comments?
In your choice of additive character is involved both in the problem and in the parametrization. That's right. I will use. What happens when you change? Yes. So that's right. So I'm answering the question. So when I do the data leaf, I fix the additive character psi. When I parameterize the representations of MP2N, I also use the same character psi, and I'm giving the answer in that spirit. Now, if you change. So the question becomes, for example, if you change the character psi in the local Shimura correspondence, how does the names of the representation change? And that is fully addressed. So for example, if you replace psi by psi c, then you may have some thing like that is going to change to some new names. Okay, and for example, this is just this. Tensor, the quadratic character associated to C. And this will change in some way that depend on some root numbers. Yeah, so this was worked out in my paper with Gordon Savin. Yeah.
Does that matter to prove the new conservation law? It's n plus n minus.
No, I use that. I use that to say that if I know the m down, then I know the m up. So, no, I don't give you proof. Yes?
To avoid the theorem being somewhat circular, in the equal rank case, you must have some alternate description, right?
No, I don't. And the theorem is not circular for the. So, if I may draw a schematics of things, is basically is like that. You have the Bessel case of GP. This was what Watts-Berger has shown. And of course, you have a LLC for SO2n plus 1. And what do I want to say? I mean, using these two plus sort of data for equal rank, right? I mean, we prove best, so the Forer-Jacobi case, and we also get, yeah, so, and then I guess then using all these things, I get data in general. So you might say that what is being claimed is that once you understand data correspondence for the equal rank case, it determines what happens in the general case.
Yeah, that's exactly my question. So in the equal rank case, you do have an independent way of saying the bijection in some terms of, I don't know, Bessel models or some other kind of parameters or something. So.
Okay, let's say this way. So so I use this local Shimura correspondence to get a local Langlands correspondence for MP2N, right? And we check that this parameterization satisfies all the sort of desiderata that you might expect of a local Langlands correspondence, except we do not check local character identities. Okay, Of course, you couldn't check that unless someone developed a theory of endoscopy for MP2, and that has been developed by Wenwei Li in his thesis. So one of my students' PhD thesis is to prove this, show that these packets satisfy the local character identities.
Do you assume that representation, do you address this question only for generic representation? It's because you want to use Gross-Prasad?
Actually, I use tempered. I assume, I don't even do it for generic. I mean, no, it's not just because of Gross-Prasad. Gross-Prasad is proof for all generic parameters, not just tempered. So, but there are other, okay, I guess one technical point was the question of when you do this seesaw thing, actually what appears here are big data leaf, not small data leaf. And in the tempered case, Muich has proved many results that say the big data is equal to small data when it's tempered. I mean, it's not really true. For discrete series, it is true. So I need those. I mean, it's a technical thing, but nonetheless, I did it. So I guess it's okay if you just move a little bit off the tempered. But, you know, I mean, it's...
You have similar correspondence of last name and first name.
Yes. Yeah, the only case we know in general is in the equal rank case, where we know it for all representation, not just tempered. But about the others, we only did for tempered.
Any other question of me? Okay, let's speak.
Okay.